the screencast is intended to show you how to use Excel and the solver tool in Excel to perform a nonlinear least square fit, that is a chi-squared fit for data. So in this particular example, we've got X and Y data, and there's uncertainty in the Y. And we're going to try to fit this data to this function that is quadratic with parameters that are the coefficients for the quadratic, the linear, and the constant terms, so A, B, and C. So before I begin, notice I also have already plotted the data. This is going to be useful. We could do this without plotting it, but then we'd have no way to tell, really, that whether our fit made any sense, or in what way we seem to have run away. It seems to have escaped and not worked. So again, we've got our data, X and Y, including the uncertainty. Got that all plotted out right here. And so the first thing we want to do is we want to make sure that our function that we're using to fit it, we'll call it f right here, we're going to write that out. And so we want to have parameters A, B, and C that tell us how to calculate this fit function. So I'll go ahead and add them in to begin with. I have an A, B, and a C. And I don't have a really great sense of what these things should be. So I'm just going to make them all 1 to begin with, and we'll see how that works out. So we'll create our fit. So it's going to be equal to A times X squared plus B times X plus C. Right? And I'm actually going to go back and revisit this, though, because I can take this and copy it down for all these other data points, too. But in doing so, if I just copy this down, it will not always refer to these data cells. The next one down will refer to the ones just below, and the next one down. So we want to make sure that those parameters are listed as absolute references. So we keep them at row 4 in the sheet. So putting the $ in to make them the absolute references, but I'm leaving the X value as a relative reference, no $, so that I can copy this downwards. I could drag it down, I could do copy and paste. If you just hover over the little square in the lower right and double click, it will autofill down until it encounters no more data in the cells to the left of it, right there. So, all right, we've got our values right there. Are they any good? Well, taking a look at my y's, they're kind of getting bigger, like my y's are right there. To get a better sense of that, though, we should add them onto our graph right here. So I'm going to right-click, select data. Let's add another series right here. And so we can tell it the series name is going to be F. Same X values as the other data. And the Y value now is our calculated fit function. All right, and we do that, and I hit OK, and OK, and we can start to see it right there. Before we go any further, though, let's make an important distinction about the way we plot things right here. So our data, original data, was plotted with just points because, hey, we measured it at certain particular values, and we don't know what the measurements were in between places where we didn't measure it. The fit function, though, is supposedly true for all values of X right here. So rather than doing points, really what we should do is have it take values everywhere across the graph. So what I'm going to do is I'm going to format my data right here. So let's take a look at my series options. So 2 things. First of all, we want to have a line that goes everywhere, and I'm just going to make it an automatic line. Notice it filled it in with that orangish-red color. And we don't need to mark the individual points. They're useful. It might be useful for comparing these things right here, but in fact, we could also just have no markers. Right? And we'll close that off, and we can see now our fit is the solid line right here, and the data are the individual points. So we look at this, and we're like, ooh, maybe not the greatest fit right here, right? It generally has kind of got that quadratic nature, but it's not so close. So I could try to adjust this by hand. I could try to make shift that value of b. I'm not sure that's improving anything when I do this. Oops. Now it seems to be getting worse, so I can make b 0, say. And hey, that maybe got a little bit closer. Still not getting the minimum right down here at the right place. So you can kind of see here with all these different parameters, it would be really a pain to do this by hand. We actually want to know, hey, is this really truly the best we can do? So what we want to do is minimize the total distance of our fit from each of the points, and somehow add that up for all of them. So for each point, we can calculate that. How far is the fit from the point is just f minus y right here. And so that's easy to calculate. That's f minus y, like that. And so that difference, how far is our fit from the data point, is called the residual. But we want to be able to somehow count the data where we're more sure that it's got a smaller uncertainty. We want to count that more than the data with a bigger uncertainty. So the way we do that is if we divide, when we add them up, if we can divide by the uncertainty, that will make that a smaller contribution if it's a big uncertainty. Another way to say that is we're measuring how far our fit is in units of our uncertainty right here. And just to make this really clear, I'm going to change this d to a delta. All right, and so here's our residual. This we often call a normalized residual. It's the residual divided by the uncertainty for that data point. So it's going to be my residual divided by the uncertainty. And then, if we think about all these, though, right, our fit is above these data right here, but it's below this data right here. And so, eventually, we're going to add up how far away we are from all these things right here. But if we were above some and below some, and we just added these numbers together, then if you were above some and below some, that could still add up to 0. And even though we're not close to the data, it would still give us kind of a minimum. And that's not really what we want. So what we want to say is if you're not hitting the data, that's always contributing, making our distance bigger. Right? And so one way to do that would be to take the absolute value of these normalized residuals. Absolute value doesn't behave very well, and there are other reasons. So instead what we do is we take our normalized residual and we just square it right there. And so that's just going to be that right there, squared. So now we can just actually take these calculations and do them for all the data all at once. And so now what we want to do is take the square of our normalized residual and add it up for all the different data points. And overall, we want to minimize that sum. We give that sum a name. That sum is chi-squared. So that's equal to the sum of our normalized residuals squared. There. And so chi-squared is a big number. So what we want to do is somehow adjust the values of our fitting parameters so that our chi-squared can be as small as possible. And we saw we could potentially do that by hand. But let's make b something that looked worse before. So I'm going to change b back to 2. And watch what happens to my chi-squared. Right now it's a little bit below 1300 if I change this. All right, so we saw that the line got farther away from the data and my chi-squared got bigger. But doing this by hand is going to be a real pain, and that's why we have the solver. So on the data menu, in the Analyze section, we can open up the solver. And so our objective is the thing that we want to adjust. That's our chi-squared, because I was already in there, that already clicked on that box that is already chosen for my objective right here. But we don't want to maximize chi-squared. That would make our fit go as far away as possible from the data. We want to minimize it, get it as close as possible. So how are we going to change the chi-squared? We are going to change the values of these parameters. So by changing variable cells, and I selected that range of cells, you could just drag across the whole range. If they were separated by some, you could hit Control and click ones that weren't right next to each other. We could add constraints if we wanted to. That's not necessary right here. Excel is kind of annoying. It defaults to always having this one constraint, make the variables non-negative. And that's not necessarily what we want. These parameters here could potentially be negative, so I'm unchecking that box. You can choose different mathematical techniques for to find the minimum. We're not going to worry about that. This method right here should work just fine for us. So I'm just going to go ahead and press solve. And we want to watch what happens to our fit, on the graph, it should get a lot closer, and we want to watch to our chi-squared. It should get a lot smaller, and we'll take a look at our value. So I'm going to press the solve button, it thinks, and it gives us the option to keep this. So first of all, before we do that, look, the fit is running much, much closer to the data right now. And our chi-squared is much, much smaller. And it did it by changing these things, which changed all these values right here. So I'm going to take this right here, and we've now hit what seems to be a minimum of our chi-squared, so that is as good as we can do for our fit. One warning I want to make is when you're looking at minima of functions, there's an overall minimum, but you can also have local minimums that aren't as low as they aren't the lowest point in the graph, but they're low compared to small things. And so to avoid getting stuck in a local minimum that isn't really the best minimum, it helps to start manually having your parameter kind of close to what they should be in the end, but then and then letting the solver take over. So we found the best fit now. One question you might have is this a good fit overall? And so chi-squared is good for, and comparing chi-squared and minimizing is good for getting the best possible fit, but it doesn't tell us is this overall a good fit or not a good fit, because, well, for one thing, it's the sum of these normalized residual squared for all the data points, so more data points will just make it get bigger, and that doesn't necessarily say anything about how good the fit is. So we somehow want to say, well, we should just divide by the number of data points. So it would be nice if we could just normalize this by the number of data points. So I'm going to make a new cell right here. This new cell is going to count the number of data points that we have. So you could calculate yourself, or you could just let Excel do the work for you. So we're going to count the number of data points I've got right here in this range. But on the other hand, we could, if we wanted to, we could make up a fitting function that had 6 parameters, or 7 or 8 parameters, and that would be able to hit every single one of these on the nose. And so we want to somehow say, hey, it's preferable to have fewer parameters. And so when we normalize it, we're going to give a penalty to the normalization for every parameter we have. So how many parameters are there? We're going to call that P. And we don't really need to count them because we know that there are 3 right here. But I'm just going to plug that in like that. 3 of them right there. Right? And so we're going to calculate a new chi-squared, a reduced chi-squared, which is just equal to our chi-squared divided by the number of data points minus the number of parameters. Right there. Okay, so this one right here is 19.5 for our reduced chi-squared. And typically what we want to say is if we are closer to 1, that is better, and smaller is better. So another way, again, to think about the reduced chi-squared is this is roughly on a per data point value, what is the difference between the fit and the data divided by, in units of, or divided by the uncertainty. And so take that squared, so it's a sum in roughly in quadrature. So if we're on average 1 uncertainty unit away, then our reduced chi-squared should be about 1. And so if you're over 1, then your model may not be doing a great job of fitting the data, or you've underestimated your uncertainty. If you're under 1, then maybe you're actually, that means that you're always coming within the error bars. That would be great, but it may mean that actually you have overestimated your uncertainty. Because we say for our error bars, they should be, they should show the range where most of the time the true value lies within that range. And so sometimes we would expect to be outside of it. So we don't expect to always be within the error bars. And so getting a reduced chi-squared less than 1 means that you may have actually overestimated your error.